Thread Overview, Part 2. What makes it special? Welcome back to Silicon Labs Thread Overview. This is Part 2 of a 3-part series. In this piece, we'll explain the key features highlighted in Part 1 that make Thread a great choice for designing IoT solutions. In Part 1, we mentioned the key features of Thread, but now let's look into these more deeply and see how Thread's providing these features. Regarding the direct addressability with Internet protocols, Thread ensures that all devices have an IP address formatted according to Internet Protocol version 6, or IPv6, which provides a 128-bit address space sufficient to cover all Internet and IoT devices worldwide, so other Internet nodes can reach the Thread devices using a specific IPv6 address via a border router. Additionally, within the Thread mesh network, each device has its own short address unique only within that HAN, such that other Thread nodes in the same network can easily find and route to one another without the overhead of 128-bit IPv6 addresses at every step. Another advantage of using native IP addresses in Thread is that the border router can easily bridge between the Thread network and another IP network via Ethernet or Wi-Fi without having to handle packets at an application layer and then proxy them manually. Because many Internet-connected devices understand the IPv6 protocol, the Thread node can construct a packet with an IPv6 header and secure its IP payload through end-to-end encryption using a secure socket all the way to the IP-connected target, be it a personal computing device or another Thread node on a different 802.15.4-based network. Using the local mesh headers in the packet, the HAN can route to an appropriate border router using 802.15.4-based links between nodes and Thread's mesh routing scheme. And the border router can simply remove the mesh headers and leave the IP headers and secure IP payload intact as it conveys the message through the Internet to the intended target device. The target then knows the identity of the Thread node that originated the packet and knows that its payload is still encrypted as it was from that originator. By contrast, a non-IP-based mesh networking protocol would be able to secure its packet and route it only to the nearest Internet gateway, and then the gateway would need to manually arbitrate where that packet's going and how the payload gets re-encrypted with IP headers and IP security on its way to the final destination. This is necessary because the originator can't establish direct IP communications or a secure socket with the destination node. One of the things that makes Thread flexible in its usage is that devices can dynamically adapt their role in the network based on stated capabilities. For example, when a router-capable device joins the network, it lets the network know that it has the ability to perform routing, and then a special router device known as the leader decides whether the network really needs another router or if the connectivity is already sufficient in that area. By default, the router-capable node joins as a router-eligible end device, or REED, meaning that it will wait for the leader to tell it when it should become a full-fledged router. During normal operation of the Thread network, an REED can also ask the leader for permission to become a router, if necessary, to promote connectivity in that area. If no leader is available at the time of joining, the router-eligible device will then become the leader router so that it can make decisions concerning routing and commissioning in the Thread network. Devices without routing capability, or those router-eligible devices that have not yet been promoted to router status, are known as end devices, and they can be either sleepy or non-sleepy, depending on whether they can leave their receiver on all the time, or instead need to put the radio to sleep by shutting off the receiver when not expecting packets. Both types of end devices rely on an active router node to relay their packets to and from other Thread nodes and beyond. Another element of flexibility in Thread networks is the dynamic handling of the leader role. While it is not uncommon to have a central authority for routing and commissioning decisions in a wireless network, this centralization creates potential for a single point of failure, meaning that if that special device stops operating or loses connectivity with the rest of the network is effectively crippled until that device returns or is replaced, and replacement may not always be feasible. Thread avoids this single point of failure by having the leader be dynamically chosen from among the active routers in the network, including any border router devices, making it more robust than some other wireless networking protocols. This handles the case where the network becomes fragmented and each half needs to maintain autonomy, even the half that no longer has a leader in it. Duties of the leader node in a Thread network include router promotion, acting as a point of reference for routing data, assigning unique addresses to incoming devices, and handling commission requests. Note that although the leader acts as a central authority for route information, all router-eligible devices, even those not currently active as routers, have a local cache of the current connectivity graph of the network. So any router-eligible device can assume a routing role or even the leader role if the need arises. This further adds to the robustness of the network. Another aspect of Thread that helps to avoid a single point of failure is the notion of the border router, the device that forwards IP packets between the Thread network and other IP networks. Thread allows multiple border routers to coexist in the same HAN, and if no border routers are available, the mesh network can still communicate locally without a problem. If the number of available border routers changes over the life of the network, the Thread nodes can adapt and make use of more or fewer of these as necessary. So if a Wi-Fi access point with a Thread radio is installed as a border router, and then the user adds a Thread-enabled set-top box with its own broadband IP connection, the HAN device can utilize either of these to reach their off-network IP destinations, even if the two border routers tie into separate internet service providers. Regarding the secure but user-friendly commissioning approach adopted by Thread, this leverages an existing device like a mobile app or web app as a user interface to the commissioning process, allowing the installer to make an explicit decision about when the network is open to adding new devices, or which devices are allowed on that network. If a Thread-capable device has its own user interface, that node can also be used as the commissioner to help the user mediate access to the network. All commissioning data, including security data, are passed over secure sessions provided by DTLS, an end-to-end security mechanism comparable to the SSL security used by most secure websites. After a secure negotiation to approve the new device and enable joining at a specific entry point in the Thread network, the new node begins a point-to-point transaction with its specified entry point, which is some existing router or router-eligible end device on the target Thread network, to obtain unique addresses within the mesh and within the subnets of the available border routers, and to obtain the current network security key through a unique link key. All communications between Thread nodes are secured via IEEE 802.15.4 MAC layer security to provide the maximum amount of encrypted data over the individual packets. Once the joiner device is fully entered into the network, it can leverage an IP layer security mechanism like DTLS or any end-to-end application layer security as dictated by the application protocol. As mentioned previously, a key feature of Thread is its low power operation, making it appropriate for sleeping devices that need to conserve energy by turning off the radios when not expecting any incoming data. Since sleepy devices determine their own individual duty cycle, the network doesn't try to determine availability of these devices, but instead relies on the sleepy nodes to poll the network to detect incoming data or acknowledgments. This polling can be to a designated parent node in the HAN, or if the application layer supports it, this check-in could be to some central repository node that buffers data for synchronous relaying to nodes that missed it. Note that these check-in messages aren't required at any fixed interval for keep-alive purposes. Each sleepy child can provide the parent router with its own expectation of expected poll interval. While the end device is sleeping, incoming messages addressed to that sleepy node will accrue at the designated parent router and will be held for up to 90 seconds. This allows parents to buffer for their children as memory permits. If a sleepy end device finds that its link to the designated parent is unreliable or non-responsive, the device can acquire a new parent on its own from the available routers within range, and the Thread network can immediately become aware of this change so that the child is no longer contacted at its prior location in the network. Now that you understand some of Thread's key advantages, proceed to part 3 of this series to learn more about how Thread stacks up against other wireless home networking technologies.